Okay, as promised, we are back with the Gaussian quadrature discussion. Um, let's start sharing it. The adaptive quadrature method may have been somewhat difficult to understand, but this Gaussian quadrature method is really very nice. And we see how the great mathematician Gauss, how people like him think about. So again, we are thinking about Gaussian quadrature because the Newton-Cotes formulae use values of functions at equally spaced nodes. The points will where we are taking the function values, they are equally spaced, and that is often not a very good thing. So the restriction is convenient when the formulae are combined to form the composite rules, but the error may be there because the accuracy will be reduced because the functions may have very large fluctuation in only some part of the interval that you are working with and may not have a large fluctuation in the remaining part. For instance, if you were looking at trapezoidal rule, what does the trapezoidal rule do? It looks at the endpoints of your interval and just joins them by a straight line. This is what it does. And then you just integrate by taking the area under that line. So that gives you a trapezoid. You compute its area, and that we declare as the approximation to our integration. But this is often not the best approximation, meaning after all, you're looking at a straight line, and almost always the straight line is not going to give you a good approximation to your graph, the graph of the function. For example, in the next slides, we are going to show you some instances where the function values are not approximated in a nice way. The trapezoidal rule, if you are taking the endpoints as the points where you are applying the trapezoidal rules. So we will also see in each case, if you change the points slightly, then you are likely to get a better approximation. So this is what we are going to see. For instance, here we see that the graph of the function is above the line, which is joining those 2 points, endpoints, and therefore you are missing out on a chunk of the integration. Whereas if you were able to change the points where you are taking the nodes slightly, then in the second figure we see that there is some part you are missing, but also some extra part that you are adding. So here the error is likely to be less. A similar picture on the other side where the graph lies below the straight line. So on one hand we had convex and concave. So in both of these situations, the straight line is not going to give us the correct answer. But once again, if you move your nodes slightly, then we see that here for between for the distance a to x1, there is some part of the graph which is above the line, and x2 to b, again there is some part of the graph above the line, whereas in between x1 and x2 the graph lies below the line. So this is going to give you a better approximation because some error is getting cancelled. Often it doesn't have to be above the line or below the line. For instance, even in this picture, where the graph intersects the line that is joining those 2 endpoints, we see that the part which is below the line is smaller compared to the part which is above the line. Therefore, we will have some error, whereas in the modified part, we see that the points have been moved slightly so that the error is minimized. So this is the essence that Gauss worked with, and what he did is that he would like to choose points for evaluation in an optimal way rather than equally spaced way. Okay, so what we are doing is that we will choose these points in an optimal way. The nodes x1, x2, xn in the interval AB and the coefficients c1, c2, cn, they are chosen to minimize the expected error obtained in the approximation of this integration. So you have integral a to b fx dx. This is approximated by summation I going from 1 to n ci fxi. Okay, but we will choose these nodes x1, x2, xn in AB and the coefficients c1, c2, cn. We would like to choose these nodes and the corresponding coefficients so that you get less error for a large set of functions. That's what we are going to do. Okay, we are not in the adaptive quadrature method. You saw that we had to choose the nodes depending on the function. Here we would like to have a set of nodes and then corresponding coefficients, so that this approximation summation ci f of xi works for a large set of functions. So what do you mean by large set of functions? We will say that they work for a largest possible class of polynomials, which means that the corresponding formula has the greatest degree of precision. This is what we are looking for. All right, so we have these summation ci f of xi, I going from 1 to n. So there are n xi and n ci, and we would like to have the greatest degree of precision. So the coefficients are arbitrary, xi are also arbitrary, but they are restricted only that they should be sitting inside the interval a b. So that way we may say that we have 2n parameters. We have to determine x1, x2, xn, c1, c2, cn. So we have to determine these 2n parameters. And if you are looking at polynomials, a polynomial of degree n will give you n plus 1 parameter, because you will have a constant term, you will have the coefficient of x square dot 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 up to coefficient of x power n. So if the coefficients are considered as parameters, then the class of polynomials whose degree is at most 2n minus 1, they also give you 2n parameters. So this is the largest class for which our formula will be expected to be exact. You cannot hope that it will be exact beyond that. The largest class, the largest degree of precision that it will have will be 2n minus 1. It cannot go beyond that. So let's try to find what are the xi and ci for which you can get that particular degree of precision. Okay. So with the proper choice of these values and constants, the exactness of that set can be obtained quite easily, in fact. So let's illustrate this method by means of an example where your n is 2. So you will have x1, x2, c1, c2. So you have 4 constants and the interval is -1 to 1. Okay, so the general situation will be discussed, in fact, in the next lecture. We will not be able to do it in this lecture. We will do it in the next lecture. So these are the constants that we want to determine: c1, c2, x1 and x2, such that this formula integration -1 to 1 fx dx, which is c1 f of x1 plus c2 f of x2, is exact for polynomials of degree 3, 2n minus 1. N is 2, 2 into 2 is 4, 4 minus 1 is 3. So 4 minus 1, which is 3. So of degree 3 or less, the formula should be exact. That means whenever the function is a0 plus a1x plus a2x square plus a3x cube for any constants, a0, a1, a2, a3, for any such a1, a0, a1, a2, a3, our formula should give us the correct answer. We will determine c1, c2, x1, x2 using this. So of course, now if you want the answer to be exact for all such polynomials, it is enough to look at the special cases, which is the constant polynomial x, polynomial x square and the polynomial x cube, because the right hand side is additive, left hand side is additive. So it's enough to work with the special cases of polynomials, which are fx equal to 1 or fx equal to x or fx equal to x square or f of x equal to x cube. So we will simply put the values of these 4 polynomials in the equation, which is integration -1 to 1 fx dx is c1 f of x1 plus c2 f of x2, and we will get 4 equations, 4 unknowns. So we hope to have a solution to them. The first equation would be, you put f of x equal to 1 in this, and you are going to get c1 plus c2, because fx1 equal to fx2 equal to 1. It's the constant function, right? So we get integral -1 to 1 dx equal to 2 is c1 plus c2. This is the first equation we got. Later we will now put f of x equal to x. then x square, and then x cube. So by putting fx equal to x minus 1 to 1, this should have been 1, the upper limit of the integration. X will give you it's a symmetric function. It's an odd function actually, not symmetric. It's an odd function. So the interval is symmetric with respect to 0. So the integration is going to give you 0. So c1x1 plus c2x2 is 0. c1x1 square plus c2x2 square is 2 by 3. And this is also 0. c1x1 cube plus c2x2 cube, which is integration minus 1 to 1 of x cube dx, is also 0. So there are these 4 equations. You have 4 unknowns. We can solve these equations. I leave the solution to you to verify that c1 is 1, c2 is 1, x1 is minus root 3 by 3, and x2 is plus root 3 by 3. So our formula will now read integration minus 1 to 1 fx dx is f minus root 3 by 3 plus f root 3 by 3. That's all. The coefficients happen to be 1 in this case, so we were lucky. But therefore, it just has to be the summation of these two. So note, it's not really the trapezoidal rule for the endpoints. It's a trapezoidal rule for some points in between. That's what we are looking at. And now this formula is correct for polynomials of degree less than or equal to 3. So of course it will be correct for constant term, it will be correct for linear term, because the trapezoidal rule is obtained using the interpolating polynomial of degree less than or equal to 1. But this formula is also correct for quadrics. So if you have a parabola or something, it will be correct for that, and even for a cubic, this formula is going to give you the correct answer. So we have chosen these nodes optimally, not using the endpoints or something or having equally spaced points. This is an optimal choice of nodes which gives us the answer. This is exactly how the general case will also work. So we will now go from n equal to 2 to higher n, and we will see how to compute these constants. So the general formula is now similar. If you are keeping the integration limits to be minus 1 to 1, you will have to solve many such equations and then you will get the solutions. But there is one more way. There is one more way to compute these xi and ci. This is obtained by something called as Legendre polynomials. These polynomials will show up again later in our course when we do the numerical solutions to differential equations. But this is one time where we are going to see some very nice applications of these Legendre polynomials. What are these polynomials? These are infinitely many polynomials. So these are polynomials Pn for each n going from 0 to 1 to 2, 3, and so on. And they satisfy two very important conditions. First condition is that each Pn is a monic polynomial of degree n. Alright, it's a monic polynomial of degree n. And secondly, integration minus 1 to 1 px pnx is 0 whenever the degree of p is less than or equal to n. So this will immediately tell you how the Pn can be computed. These Pn are called the Legendre polynomials. They satisfy some very nice differential equations, and so they are studied with respect to those, but they also have these very nice applications. How can we compute these? We know that P0 is a monic polynomial of degree 0. Now, any polynomial of degree 0 is a constant polynomial, but this is a monic polynomial, so highest degree coefficient has to be 1. Therefore, P0 is equal to 1. How do you compute P1 now? P1 is a monic polynomial of degree 1, and for any polynomial of degree 0, this integration minus 1 to 1 constant times P1 has to be 0. So P1 has to be an odd polynomial definitely, and therefore it cannot have any constant term, and it is monic, so it will have to be P1x will have to be equal to x. P2x can be computed as x square minus 1 by 3. Once you have P0, once you have P1, Using them, you can compute P2. It's a polynomial, it's a monic polynomial of degree 2, such that integration minus 1 to 1, P0 P2 is 0, integration minus 1 to 1, P1 P2 is 0. That will give you two conditions, and using those two conditions and the monicity will tell you that the highest degree coefficient is 1. So you have to only compute the two coefficients, which can be computed using the two coefficients can be computed using the two conditions. P cube happens to be x cube minus 3 by 5x. Remember, it has to be an odd function, so it cannot have any even degree term. And similarly, the P even will be even functions. They will not have odd degree terms. And P4 is x power 4 minus 6 by 7 x square plus 3 by 35. So these are the ways we can compute these Legendre polynomials, but what's a big deal about them? The big deal about them is that these roots of these polynomials are very important. So the roots of these polynomials are, first of all, distinct. So if you are taking Pn, which is a polynomial of degree n, it will have n distinct roots. So you have n nodes, but we will come to nodes later on. Let me not give you the secret right away. These roots lie in the interval minus 1 to 1. That's very good. We have our roots lying inside the interval that we are looking at, minus 1, comma 1. They have a symmetry with respect to origin. So these are very nice to work with. They are symmetric. The first root and the last root, if you are putting them in the decreasing order or increasing order, then there is a symmetry about them. So whenever you are looking at polynomials of odd degree, 0 has to be a root. And that is quite clear because they are all odd polynomials. So they will not have a constant term, they will not have x square terms, and then x will have to divide them. So you see that 0 has to be a root. And most importantly, they are the correct choice for determining xi and ci. So what do I mean by this? Let's phrase it in the form of a theorem. Take your Pn, take the n distinct roots of the Pn. Remember, Pn are the Legendre polynomials now. And for each I, you define these coefficients Ci, which are the integrations minus 1 to 1, product j going from 1 to n, but j is not equal to I, x minus xj upon xi minus xj dx. This looks like the Legendre polynomial that you have, right? For given these nodes x1, x2, xn, the integrand is the Legendre polynomial. So we are taking the integration of the Legendre polynomials for these nodes. And once you have these xi and ci, then for polynomial of degree less than 2n, this formula is the exact formula. So you have integration minus 1 to 1 px dx equal to summation I going from 1 to n ci pxi. So this theorem makes our job very simple, because if you wanted to get the formula exact for, let's say, 2 into 15, then you should compute the polynomial p15, which is the Legendre polynomial p15, compute its roots, and once you have those nodes, you compute the corresponding coefficients, and then you are done. And it does actually seem like a lot of work, because computing P15 on the go is not easy. You have to compute P0, P1, P2, P3, P4, and so on. So all those need to be computed. But you don't really have to compute them, because they are so useful that they have been tabulated extensively. Remember that these xi and ci, they are independent of the functions. We are looking at xi and ci with the property that the degree of precision of the formula is 2n minus 1. Right? So these are independent of the function. These are some given minus 1 and 1. That's a very important interval. So on that interval, we are looking at these coefficients and the corresponding nodes, and they have been tabulated extensively. You may just use them off the shelf. They are there on the shelf. You go to the shelf, pick those formulae, take those nodes, take the corresponding coefficients, put them in your values and obtain the answer for that. For instance, the P3 degree 3 polynomial, the nodes and coefficients are as follows. We see that already the nodes are symmetric with respect to origin, and indeed the middle one is 0, the first one is positive, the third one is negative, and because the xi are symmetric, the corresponding coefficients are also symmetric, and so you have these x1, x2, x3, c1, c2, c3. These are going to give you the correct answer for polynomials of degree up to 5, which is 3 into 2 minus 1. So let's suppose that I want to use these values and compute the integration minus 1 to 1 e power x cos x dx. Suppose we want to compute this using these values. Then what do we have to do? We take the integration, and this is approximately the sum of these three values. Remember the midpoint, the middle one, the node is 0, so e power 0 and cos 0, those are all 1. If you were instead looking at sine, then the middle part will not even exist. Okay, so you will just have two terms for x1 and x3. Those will be the only two terms. But here our x2 is 0, so e power 0 will give you 1, cos 0 will give you 1, and the remaining x1 and x3 are put here. If you compute this answer, this is 1.9333904. Whereas if you were to compute the actual answer, which I believe you can do much better than me, the answer would be 1.9334214. So the answer is quite good, definitely for first 4 digits or first 3 digits after the decimal points, and even for the next digit 39 and 42 are not very far. So this the absolute error is less than 3.2 into 10 power minus 5, which is quite good, right? So this is how the Gaussian quadrature method helps us in computing the approximate answers to integrations, definite integration. But this was for minus 1 to 1. And we want to do it for a general interval AB, and we will do that in our next lecture. So there should be something interesting left for our next lecture also, and this is what it is. So hang on, we are going to do more and more interesting things. Thank you.